Hello guys, welcome back to the channel EC TechNest. In day 16 of the 100 days Verilog and digital design series, we are going to discuss today about flip-flops with synchronous and asynchronous reset. Also, we are going to discuss about a very important topic, that is a reset synchronizer. It is one of the important concepts in timing analysis. Let us see, what is a synchronous reset? A synchronous reset is sampled only at the active edge of the clock. First, you must be knowing what is the edge. This is the positive edge and this is the negative edge or the falling edge. Even if the reset signal is asserted, the output will not change until the next clock tick. That means if you are given in your code that the code has to change at positive edge of the clock, so it will only change during this time and it will wait for the whole next cycle, and again at this positive edge of the cycle, it will again reset it. Logic behavior. The reset signal is treated as just another input. What they mean to say is, instead of giving the reset signal as a clock, we use the same inputs. Like if you are giving for a D flip-flop, alongside D input, you are giving reset as another input. Only if you give the reset input as high or reset is equal to 1, then it will act as a reset. That means your output will become 0. It filters out glitches on the reset line and ensures the entire system resets at the exact same time. So synchronous reset has less glitches and it will provide a good result. But there is a con in that. It requires an active clock to work. It means this clock has to keep ticking. If this is not working, the system cannot be reset. See, this is how D flip-flop with synchronous reset looks. So it is called as a D flip-flop with synchronous reset. So what happens here, we need to understand that if a rest a reset is 1 dash b naught. If see if you're this is like acting like a select line. This is a mux, right? 2 is to 1 mux. So this is acting as a select line. If your input select line input is 1, that is your active high, so whenever reset is 1, it will become 1 dash b naught. If it is 1 dash b 0, that means if your reset is 0, this d input will be given here and this will act normally like a D flip-flop. So whatever is your input will be given as the output. See, always at positive edge of the clock you will begin. If reset is 1, your Q output will be 0, or else it will be the same as input D. This is what we mean as a synchronous reset. For asynchronous reset, this reset takes effect immediately, regardless of the clock state. As soon as the reset signal is asserted, the output is forced to the reset state. It means that here in asynchronous reset, it is not dependent on the clock cycle. Even if the clock stops ticking, you can reset it. How does it work? The reset signal is connected to the clear or preset pins of the flip-flop primitive. So whatever your reset signal is there, it is directly connected to the inputs. So it will clear it out. So it means it will become 0. So your output will also be 0. Because in a D flip-flop, whatever is your input, that will only come as output, right? So the system can be reset without running a clock, which is critical for power up sequence. This is what I had told you in the beginning. Here, but it is very sensitive to glitches. If a small noise spike occurs on the reset line, the circuit may reset unexpectedly. It means this is very sensitive to noise. If there is a small noise or any environmental problems, the flip-flop will automatically get reset. That is one thing that we need to avoid. This is your D flip-flop. What happened there? We had a separate mux that decided whether I have to give the reset or not based on the select line. But here you're directly giving in the reset as an input. Here it is taken as input. So it is clear input here. Always at positive edge of the clock or positive edge reset begin. If reset is 1, your Q dash will come 1 dash B naught. That means your output is 0. Else it will be the same as input. It means your output will take whatever is in the input D. Here we arise with a problem in asynchronous reset. That is, the biggest problem with asynchronous reset is that they are asynchronous both at the assertion and deassertion of the reset. The assertion is not an issue, but the deassertion is the issue. So what we mean to say is if the asynchronous reset is released or near the active clock edge of a flip-flop. So consider this is two clocks, clock A, clock B. Here this is the uh, active clock edge. That means it is a positive edge. And here if you're considering it, it is very near to the what do I say? This can if this is the reset, it is very near to the falling edge also, right? Here. So what happens is it creates a gap. So exactly if I want to tell you here, here there is a shift between 0 to 1 occurring, right? From here you have the falling edge. Again it is going to the rising edge. So at this time you have the state going from 0 to 1. Here what happens when you expand it, this 0 to 1 state gets expanded. So the output of the flip-flop, if it comes in this stage, right? This is the metastable state. It can either be 0, it can either be 1. So it is termed as metastable state or unknown state. We'll see the comparison and we'll also see how this metastable state can be solved. Synchronous reset only positive edge of the clock. Here asynchronous you can use positive edge of the clock as well as positive edge reset. Timing happens on the next clock edge. Correct. On the positive edge of the cycle it will happen. It happens immediately because it is not dependent on the clock. It can happen immediately. Synchronous reset needs a clock to function. This can work without a clock. As we discussed, this is not that sensitive to any of the noise or something, but here asynchronous is very sensitive to noise. It can suddenly reset. Circuit size is slightly larger because we are adding an extra mux, right, in synchronous reset. In asynchronous reset, it is generally smaller. It uses built-in flip-flop pins. That means the reset is given as input pin. Here the problem is reset recovery and metastability. If you use a pure asynchronous reset, the release, it means it is coming out of the reset phase, deassertion phase. The reset signal might happen dangerously close to the rising edge of the clock. It means your reset is getting scheduled, but as well as your next whatever operation you have to perform, that is also happening because of the rising edge. This violates the recovery time of the flip-flop. It means it will enter a state where it is doing the operation also, but also it is doing the reset. So it does not have the recovery time for the reset to be again set to 0 so that it can perform the operation, leading to metastability. So it is confused whether it is 0 or 1, 0 or 1, where the output hangs between 0 and 1, potentially crashing the state machine. The flip-flop will not work as per intended. So, since your FPGAs and all have multiple flip-flops, this is one of the mechanism, the reset synchronizer. It is also called as synchronized asynchronous reset. What it has is it consists of two flip-flops connected in series. By seeing this, can you remember something from our previous video? At the end, we discussed about master-slave flip-flop. Here also it is very same thing, but the only change is there we have to give an inverted input to the slave flip-flop. Here we are giving the same clock cycle. So let us see how it works. Assertion going into the reset phase. It means reset is 1. The reset signal stays asynchronous. As soon as the master reset hits, the output of the synchronizer goes to 0 immediately, resetting the entire chip. It means here you connect your VCC to 1. So based on this, let us consider here it as the previous state. So based on this itself, you will give your asynchronous. It will be opposite to this. Here, when you are giving, you have to see that this clear signal is going as 1, but when you are giving to this, it will go as 0. I'll explain you in detail after telling about the deassertion. Deassertion is leaving reset. One minute. When the master reset is released, the signal must pass through the two flip-flops. It will be only released to the rest of the design on a valid clock edge, ensuring every flip-flop in the system wakes up at the exact same time. So when this master flip-flop synchronizer goes to 0, this will push whatever is in the master flip-flop to the slave flip-flop. So you will get only a single synchronous reset. You will not have that metastability where it is shifting from 0 to 1. So your problem of the metal stability or the reset recovery time is reduced because you are giving only one input to the flip-flop. If you want to know the whole diagram, I'll just explain this. So what is happening is this whole reset synchronizer, it will be connected to the D flip-flop here. So whatever reset you had to give to the D flip-flop will be given through this. This will be called the master synchronous reset or the reset synchronizer. Here you are giving asynchronous reset, but when you are getting the output, it is synchronized. So this is how you will get the name synchronized asynchronous reset. So hope you have understood how we solve the problem of reset recovery and metastability. If you have any doubts, feel free to put it down in the comment section. Thank you.